Elliptic Curve Cryptography, or ECC, gives much shorter keys than RSA at the same security level. It powers modern TLS, X25519 key exchange, and most blockchains. An elliptic curve is the set of points satisfying the equation y squared equals x cubed plus ax plus b. In our example, a equals -1 and b equals 1, a smooth, non-singular curve. Adding two points P and Q is defined geometrically. Draw a secant through P and Q, the line meets the curve at a third point. Reflect that point across the x-axis to get R, the sum P plus Q. Scalar multiplication k times g means adding g to itself k times. Computed efficiently with double n-add in only about log base 2 of k steps. Given g and k, computing kg is easy. Given g and kg, recovering k is extremely hard. This is the elliptic curve discrete log problem, ECDLP. ECDH key exchange depends entirely on ECDLP hardness. Alice picks secret A, publishes A equal to a G, Bob picks secret B, publishes B equal to BG. Each computes the shared secret S, Alice computes AB, Bob computes BA. They match because ABG is commutative. For 128-bit security, RSA needs 3072-bit keys, while ECC needs only 256-bit keys. Roughly 12 times shorter, which is why TLS, MTLS, and blockchains all migrated to ECC. Unfortunately, Shor's algorithm also solves discrete log in polynomial time. Per Rodelier et al., breaking P256 requires about 2,330 logical qubits, fewer than RSA 2048. Shorter keys mean broken sooner. ECC is faster and more compact than RSA at equivalent strength, but both rely on discrete log, and Shor breaks them both. Up next, AES, our symmetric workhorse, and the Grover threat.